Okay, hi guys. I actually like the animation. It's pretty awesome. So we're here to talk about in-memory computing and distributed systems. The problem is, and I'll be honest with that, the talk is normally an hour, so I squeezed it down to 30 minutes after I recognized it's like 30 minutes. So let's see how it works. First of all, we're going to play a game. So I ask a question and you say yes, okay? So did everybody read that? Perfect. I love that. So this is hopefully what we're not going to do when we're talking about distributed computing. It's kind of distribution, but hopefully not the way we're going to implement that. So who's that dude? I'm Chris. Well, the official name is Christoph, but don't try that. In most countries, it doesn't work. I'm a kind of Twitter fanatic because I am about 1,000 tweets per day or something. Almost like 10 years by now, Java development, mostly in the recent past, JVM internals as it was already said. Garbage collector optimization protocol, TCP protocol optimization. So everything that makes systems fast and distribution fast is kind of my world. I worked in the gaming industry. I worked for Ubisoft. I worked for HRS, which is travel management. And our ex-vice president of marketing had some roots in Japan, and he came up with the term for me. And so I started to get the domain hazelcast.ninja. So this ends up in my blog, if someone's interested. Okay, so get to the real thing. Distributed computing. I guess everybody has its own data center at home, right? So we have an old PS3 by now, maybe a PS4. We have some old computers somewhere around, maybe a laptop, maybe a MacBook by now. And since we're moving forward, and I'm referring to Bruno, he will show some IoT things. You might, in the near future, you might have a second data center at home, which is like your kitchen. So you have some power bank and a toaster, a kettle, and obviously, in the near future, you have a power grid as well, which is pretty nice though. But okay, what does distributed computing really means? We're talking about in-memory computing. So don't we waste memory keeping all the data in memory? Obviously not. As you can see on the numbers and access times, the main memory is pretty good. It's not as good as the access times in L1 and L2 CPU cache, obviously. But for example, if you try to send a packet between California and Amsterdam, and back, you see 150 milliseconds latency. This is probably not what you want to do all the time. So the thing is, keeping data in memory speeds up the access a lot, even though against the hard disk or nowadays the SSD systems. Keeping data in memory is also not a big problem anymore. So the table starts at 1980, and we see that the typical amount of RAM always grows, but the price is going massively down. I mean, 16 gigabyte RAM by now is like an Apple or something. In the short future, if you look out to the near future, you might see servers with 512 gigabytes of RAM with no problem at all. So the idea is, or the general idea is to scale out and not scale up. There might be some competitors not totally agree with that. So for example, there's always a company who can sell you a bigger database if you, and coming to the limits. But the way to go is most of the time scaling out, using commoditative hardware and start up more servers. But it means you have to distribute data, you have to do distributed computing somehow, you have to distributed queries. The guys at from Betfair just said, talked about the CAP theorem, and the P means obviously partitioning. So you have to somehow share the data in the cluster. So distributed computing is mostly about data distribution, which is partitioning, or if you still have some old database admin, you can ask him about relational database sharding. He probably will kill you. I'm not sure if you want to ask him about sharding. So, data distribution. I tried to come up with something very simple, a very basic example. I'm not sure how many Java coders are there. Quite some. Okay. So the code shouldn't be that hard to understand. So there is some code which is Sunny TechHub, and whenever someone wants to have a Hazelcast T-shirt, he put the code together with his address in that URL. But the main point here is you have a map, and you put the code and the T-shirt delivery into the map. And what actually happens underneath, at least for Hazelcast and a lot of other systems, is you have this code, and you somehow have to create a hash code from the key. And the hash code is then used together with, for example, a partition count to get a consistent distribution. So whenever something happens, you know exactly where to find or where to store that key. That means the hash function itself must be consistent. Every node that is ever going to hash this key must end up with the same hash code result. The partition count, in the easiest way, should be consistent or should be constant from the startup of the system to whenever you shut it down. Obviously, you can change it afterwards and restart the system. There might be also an option to do this at runtime, but then you have to remigrate all the data because you end up with a different partition index to send the data to. And the most important thing about consistent hashing is you can calculate it wherever you want to. It can be another cluster node, it can be a client system, and if you have some smart routing enabled, for example, on clients, you don't have to have an additional hop just sending it to one of the cluster servers, and hopefully he will reroute it to somewhere else. But if the client knows about the partition system, he can send it to the right node immediately. So I hope that wasn't too hard to understand. So far, any question? Okay. The next big thing about distributed computing, and the name obviously makes it clear, is parallelized processing. Parallelized processing means you want to have multiple machines, in this case multiple humans, doing the same task, a smaller chunk of the task, but always in parallel. So again, this time not really Java code, it's not Scala code, it's just something I came up to squeeze it on the slide. You want to sum up all the numbers. So there's a 100,000 element array, and what we do is for each of the number, we just generate a random int. So we end up with an int array of 100,000 random elements. We then, and this is the important thing, we split it up into smaller chunks of work, and for every chunk of the work, we use the sum function. So imagine these blocks for each would distribute it into the cluster, or even easier, what most people have really at home is like a graphic card. A graphic card can do massively parallel processing. So you could send each block to another graphic card's core, and all of them would process the chunk in parallel. And eventually, what you do is you get a sub-result, and then you sum it up again. The nice thing, though, about the last point is you might split this sub-result again and do some more processing. So even here, we have like a very few basic points that we need to keep in mind. You shouldn't have any kind of mutation. Mutation is bad for parallel processing because it means you have to guarantee memory visibility, you might have to resubmit or redistribute data. But if you just split it up, you have a fixed block, you can send it wherever you want to. You just send the operation and the data, and everything happens automatically. The second point is we have independent computation. And this only, as I said, works if you have no mutation. Because then every chunk of the data is completely independent and can be computed independently. And as I said, the last thing is, if you, for example, have fork join pool, and you look into the implementation of the Java fork join pool, you see it might split up the operation even further and in smaller chunks and even smaller chunks. And that way you can nicely distribute it in the same computer, over the graphic card, over multiple computers, maybe even worldwide, like Google does the search on their search results. So again, I hope that wasn't too hard to understand. Well, I'm from Germany, so I guess one or two people might recognize her. Probably the best photo of her. So far, any question? Good. And the biggest, and another very, very big point about distributed computing, and this is especially true for Oracle Coherence and Hazelcast, is the third part of what people normally do with the distributed cluster, which is caching. Caching means you keep data in a system which is fast to access, has quick round-trip times, maybe it's even in the same process. So there are multiple versions of caching. You can have like a cache inside of your application. You can have a database and a cache system somewhere in between, but you still get the speed because you don't have to query down to the slow database, which is doing something totally different, like write operations and something. And there are also multiple ways on doing caching at all. So the typical solution for implementing caching or for using caching in Java applications at least is a thing that a lot of people do, and they just rolled their own implementation. Who did write his own cache implementation so far? 1, 2, 3, a couple of, yeah. So, I mean, it's obvious. A cache is simple, isn't it? A cache looks pretty much like this. You have a concurrent hash map, and somehow you wrap the put and get operation. Would anybody disagree on that? Is a cache that simple? You disagree? Yeah, not exactly. You're halfway through disagreeing. OK, so let's say we want to make it a bit more complex. You don't need to read the source code anymore. That's the reason why I took a screenshot. So a cache obviously is not that simple. Sure, you can do put-get operations, but normally a cache expires, or elements in a cache expire. So you have some TTL, time-to-live operation. TTL, OK, so we not just store the key and the value, but we have to store some metadata that would be readable somewhere over here. I have the value, and I have a creation time, and I store the TTL, or the time when the element actually dies. OK, so far so good. At that point, operation might kick your ass and say, well, you have a cache and it expires, but why does your memory is always growing? Well, yeah, sure, we don't have auto cleanup, so we just remove elements, dead elements, whenever we run out of memory. OK, so you come up with something like an auto cleanup. Auto cleanup is amazingly easy. Everybody knows that you have a thread is running in the background, looking through the elements, and eventually might find something that is expired and removes it. And I made this bigger, so what is wrong with that implementation? And everybody who ever wrote a cache might recognize the problem. So let's see if someone can find a problem with that. I mean, it's just a couple of lines, right? It can't be a big issue. I guess he has the right idea. Okay, I'll tell you. So the implementation has big On runtime behavior. That means imagine this iterator runs through 5 million elements, 500 million elements, depending on how many elements you have. And maybe the task runs like every second. Do you think the system has any time to do something different than just expiring data? Maybe not even expiring data because nothing is expired? To be honest, something like that was even hidden in Hazelcast. And when we found that, it was like, oh my goodness. And the way we found it is we created a load testing tool. And everything looked amazingly good in the unit test. And whenever we started the load testing, the system became 100% CPU usage, and nothing else happened anymore. And we're like, what happened? And we found that, and it was not only that, it was even worse. Did anybody know, or does anybody know the difference between executors, schedule executor service, schedule like fixed rate, and schedule with fixed delay? Right, so fixed rate means if you say execute that with a fixed rate of 5 seconds, it will do that, even if the task is not yet finished. If you do it with a fixed delay, it will wait for the task to finish and then schedules the 5 seconds. So imagine that with 500 million elements and a fixed rate of 5 seconds. We ended up with having, I guess, 10 or 15 threads doing nothing else than not expiring any data because the TTL was like a long max value or something. So it was just iterating and iterating. But the problem is that was probably the answer you would get in the end if you ask someone else. So what should be the right way to do it? The evolution of caching that is not self-written is proprietary caches. There are a lot of proprietary caches in the past, or even though they are still existing, like coherence is still proprietary, and I think it won't happen, it won't change in the near future. He's shaking his head. The other option, open source caches, there's EHCache, there's Hazelcast, but there are also a lot of other things you can do with caching. And then there are commercial, and commercial does not mean they have to be proprietary. For example, Hazelcast has open source and commercial versions. And then there is a fourth category of caches, which is the stupidly expensive one. This term is not my creation. Some person at a conference came up with that term, and I love it. So what is the option? We had a lot of Java developers, and did anybody of the Java developers already hear about JCache? Not yet, okay. So the solution to that problem and to unify all these different types of caches is JCache, which is the new Java standard for caching. And the nice thing about JCache is there's a specification which says, here, this is a cache, and it looks exactly like that. And this is how a cache behaves. And it doesn't matter if it is coherence, EHCache, Hazelcast, or anything else underneath. And this is what I like about the Java environment. We have a lot of specifications which tend to provide you. It doesn't always work, but it goes in the right direction at least, to show you that there is a common superset of things, and you can do this with any kind of vendor, and you're not set to use a vendor. You don't have a vendor lock-in, sorry. And I think this is a very, very important part of distributed computing. Distributed computing is every time is a cache. The second you store data in memory, you have something like a cache. You might not expire data, but you end up having the data in memory. If you have it in front of a database, you obviously have a cache. So again, I guess that feels like success. And now I have 5 minutes left, so we'll make it a 3-minute marketing pitch. Let's talk about Hazelcast. Talk about something serious, right? So Hazelcast is pretty easy to explain in 5 facts. We're a distributed computing environment. We have the Java Collection API, which means you can have a drop-in replacement for Java maps, lists, set, queue, and all those data structures you know from the standard Java API collections. We have the same thing for the Java concurrency API as far as it is possible. Like there's an executor service which makes distributed computing extremely easy. You use the executor service you know from Java, you put in runnables, you put in callables, and they get distributed in the cluster immediately for you. If you have a callable, you can even wait for all the results to be computed. We have distributed transparent data distribution, which means we do exactly what I showed earlier. We have a consistent hashing algorithm, and you just put in data in Java objects, whatever it is, and as long as we kind of figure out how to serialize data and to send them around, we're happy with that. As I said, we're a drop-in replacement most of the times. Not for everything. If there's no interface, you can obviously not replace it. We also have like extensions. So you have like a Java concurrent hash map, concurrent map, and we have IMAP, which extends that and adds features like distributed query and kind of things. So stuff you would expect from a distributed environment to happen. And I like that Rod Johnson is one of our board members. Who knows Rod Johnson? The inventor of Spring. At least one guy knows the name. So he's the inventor of Spring. And he came up with the idea of JE is too complex. And I mean, if we look at JE nowadays, he seemed to be right, or he seemed to be right at least. JE is going the same direction as Spring, and this is definitely the best step in the JE development ever. And he said about Hazelcast is disruptively simple, which means for me it is so simple to use that sometimes people using it really like a local data structure, which is also not a good thing, maybe. I had a nice example. I showed it yesterday. I should put it into the slide. It was quite nice. But the important thing is everybody knows that problem from mobiles. Like every mobile developer or mobile vendor had its own kind of power plug, data transmission plug, whatever. But nowadays, everybody's moving to micro USB. Micro USB, yeah, I guess so. So Hazelcast and the Java Collections API have already the same plug. Now we have JCache, which means all of them have kind of the same plug. And this is, for me, does anybody disagree that the micro USB port for your mobile is a bad idea? I don't think so. And I hope in the future we have like a common API in Java for distributed computing, which makes it easy to do distributed computing. The executor service, for example, is not the best matching idea since you get futures, and what happens if you cancel a future that does a put operation? So there are some things that are not really clear to clearly defined because the API is not designed to do distributed computing. But it's the easiest way to do it at the moment for users. So my personal point is, and I think we definitely need more of that, I don't want proprietary APIs. I want to have open standards. And open standards mean we want to be happy. And for Hazelcast, time to be happy means, for me, it's Apache license. You can download it and go just download it, get started, try around. If you use the JCache implementation, you can try it against EHCache. You can use EHCache in local systems and Hazelcast for distribution or coherence or whatever. And just go to hazelcast.org and, well, you can do it, I guess. So that's it, and I'm absolutely in time, 20 seconds left.